Present and all of you who are on the interwebs. Welcome to the afternoon session of the August SVFIG meeting. I guess it might be more effective at this point to look at the screen than at me. So this amused me greatly, and we were talking about MagSafe before we started, so this part of this is actually relevant. Back in July of 2012, Ting gave a YouTube presentation because he couldn't be at the meeting. So if you're still interested in Launchpad eForth, you might want to have a look at that. There was another video behind here from the folks at the folks at 4eForth or 4EuroForth, who did a brief demo back in the back for that same meeting, and it was here a minute ago, and I lost track of it. Before lunch, we were talking about a few things that you can see at the Stanford University campus. For those of you who are physically present or reasonably nearby, this looked really interesting to me, and it starts September 4th, and it ends before the September meeting, so pretty much out of luck if you're planning to come to a FIG meeting and see this. But it involves supercomputing, digital art, and education in physics, chemical physics. Okay, sure. We were going to go see this, but there wasn't a wave of excitement and interest. So all you ne'er-do-wells who aren't interested in democracy are going to get sent to Gitmo or some darn thing. I don't know. So, anybody got anything new and interesting that they care to briefly tell us about? All right.
Well, we're going to lower the bar. Docs, Al-Qaeda on steroids. Al-Qaeda on crack. Get that? Get that? So now, anything relatively interesting?
Okay. So, when I'm not looking at XKCD or Dilbert, I might be looking at reruns of user-friendly. So this is computer humor from, oh, maybe the 80s. Yeah. So I recommend that to you. And furthermore, there's more. I'm just gonna amble around a little bit here and tell Dennis that I think he's the first presenter. So you might want to start moseying towards the front of the room because it looks like the 0th presentation is. So how many of you were able to copy that? No, I just read it on the screen myself. Close enough. Anyway, these guys from 4E4 were kind enough to send this little demo video of their system to the exciting 4E4 Launchpad MSP 430 day that we had in 2012. So Sam was criticizing their implementation of Morse code. So we're going to take a short break while Dennis moseys on up and prepares to give his talk. And it just goes to show you. What?
So if you're done talking,
I'm done.
I'll disconnect your voice.
Consider my voice disconnected.
And yes, we are alive. Okay. We're going to go here and pump this up a little bit. Okay.
Are you broadcasting on YouTube as well?
Yes, I am broadcasting on YouTube as well. Why aren't I displaying on screen though? That's disconcerting. Oh, there it goes. There we are.
And in reverse.
Of course. Of course. Why would it be anything other than reverse?
That's only for the local line. It comes out right.
Yeah. No, I didn't want to chat. Screen share.
Microsoft released a bunch of patches on Tuesday to their automated update.
Yeah.
and then said, I guess not to everybody, but said that, you know, those are really bad, and you should actually uninstall them. Even if your machine is working fine. And it's apparently this recommendation to uninstall these updates is buried in the FAQ.
Yes.
If you're interested in hearing more about this, let me know. I'll show you the risks article. Great.
Yes, that was a good one. The key to it, what the heck is the Windows kernel doing messing with fonts, different font tables? That's what it comes up. If there's a link in a font table that it wants to mess with, it blue screens. You know,
It will brick your computer.
Well, the kernel does have to access the font tables
right, to get the true type font.
to put anything on the screen, any character.
And if you have put something in there, or an application did, that has a link, that link isn't interpreted correctly by the kernel, and the whole thing crashes
Great.
during boot.
Great.
You can't get back.
Oh, wonderful. Don't we love Microsoft?
Yeah, I really like it when it was some of the old straight raster shit.
Ready to go?
As soon as you're done.
No, it's on top line 4.
Maybe just make it bigger.
How's that? Is that better? We can probably go one tick further. Yep, that will work. Okay? Cool? I'll see how far I can get away with that. Okay. Somebody on SVFIG decided they wanted to know how to get started with GA144. And seeing that I've done this a few times before, I decided, okay, I can go through those steps. They're really very easy. You start out with, if I can get the right picture. What do I do here? Oh, stop sharing. Let's stop sharing for a moment. And it's not a really good picture because I still haven't worked out good camera yet, but that's the evaluation board that has 2 chips on it. There's one there, and among all those wires, and there's one down there. And a whole bunch of open space, and when you get the board, none of these wires are there or none of these parts are there. You've got to solder almost everything on, except for the chips, which is a good thing. Those have been watching my travails over the years. I went to a smart board and tried that, and it did not work well. I finally blew it up. Not on purpose, but sometimes I wish I had. The evaluation board is a very good board, and they provide schematics, and I'll show you where those all are momentarily. So if we go back to, which one of these? Oh, this one. Share. Okay. And I put this up on my blog just because it was an easy way for me to organize all these links in one place. The green arrays support takes you to this site, which is where almost all of the links that I am describing are located. They're almost all here. That's this link. You need the software. The software is a very nice piece of software that gets you this bunch of files in a green arrays directory. And in those files, you've got eForth, which I haven't used much. There's also a polyforth now, which is the PF, which I haven't used much either. I've been working pretty much on green arrays directly within their simulator. And it used to be called MachineForth. Is it have a name anymore, John? Does MachineForth, is it still called MachineForth? The machine code.
I think so.
Okay. I can never remember. But all these other nice languages are very nice. Bill's here today too with eForth. And yeah, they're nice. I don't use them much. They get in my way. But it does mean that now you've got over here on your folder, on your directory. Now, is that coming out? Probably not. I need to decide more what I'm sharing here. Oh, let's share the screen and see what happens. Yeah, that tends to do that. So we will get out of that and put this up so that we don't even have it in the background there. And so in the green arrays EVB directory, you'll have this guy. And it's the main executable. And you can click him and you get what is typical of ArrayForth. That's ArrayForth running. Nice little system. And
It's an ArrayForth. It reads an ArrayForth, but on top the caption bar it says ColorForth, which is confusing.
There's a lot of things confusing about the GA1, this whole chip line, that you got to know history. ColorForth is Chuck's fourth. Chuck has been doing ColorForth for many, many years. It is what OCAD is written in, which he used to design the chip.
Okay.
ArrayForth is a compiler and simulator made to support GA144.
That is in ColorForth.
That runs on ColorForth.
So ArrayForth is not a language, it's a tool, set of tools.
Well, it describes the language and the
Yeah.
environment.
Yes.
The language is different from ColorForth or not?
No.
No.
Okay.
ColorForth is the IDE. ArrayForth is what's running in the IDE. Okay? Now, when you do this, you've got two windows. You've got this window, which is a little background debug window that tells you some useful information. I've never found it useful. But supposedly, every so often, if you have problems, you'll see something here. And I've had problems, and I've seen something there. The ColorForth is where you're going to go in most of the time. It's an interesting language, and we'll get into that in a moment. First off, you might, on a Windows machine, be interested in putting this to the taskbar. That has a little bit of interesting things that you've got to do, you may need to do also. And you may need to move where the stuff is located. So I've had to do that, and I've actually got another one that is my working copy rather than the one that we're using right now. And that's just Windows stuff. Okay, so we're going to actually get out of this one. You will notice on this that if you exit here, this guy doesn't go away. So you typically want to say by within ColorForth, within ArrayForth. And then both windows do go away nicely for you. You'll notice as you start this up and you start typing things that you've got one over here, the ASCII of what you type, and this is actually the Huffman encoded of what you're typing, of the characters. And it will go into different elements on the stack, which you want to sort of get rid of. An error, just like in most forths, will get rid of them. Okay, so you now got ArrayForth up and running. And you've got your evaluation board. And if we go over here, where was that? Oh, stop sharing. Yes. You notice down here at the bottom that you've got 3 USB connectors. The one here on the end is the host GA144. The one in the middle is the eForth one, or secondary. I haven't found much use other than eForth yet. And my eForth is not loaded on my system, so I can't show you eForth. And the third one is the target chip. And that's where I use mostly, is the third one. If you go into, now I do need to share
there
this.
There are 2 chips, host and target, and there are like 2 USB connectors for one of them, separate.
There's 2 USB connectors for one for the host chip, and only one for the target chip. Okay. Now if we look at Device Manager, because you are going to have to deal with that, let's actually turn it on. And go away that. And hopefully I still have, when I go back there, I'll see it. Notice we have 3 USB ports. Now, let's go over to, where? Here. The first once you've got things installed, the first document that you want to get into is this AN Application Note 004. And that's getting started with the evaluation board and going through how to check out this board. Nice picture of Chuck in his t-shirt. And giving warnings things, and you should observe all the warnings and where all the jumpers should be and all this, and checking the power supply and blah, 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 and all this good stuff. And the first thing is say, go try eForth. Well, I've wiped both chips with various times over the years, and I can't remember how to flash eForth again, so I'm not going to show you the eForth demo. It's not working. However, the nice ones that I do use frequently whenever I go back to the board, is things that allow me to see if the chip is actually working. If the chips are working. There are some self-tests. So we can do, and if we go back here to the, where was I? No, that wasn't, oh, that was the wrong one. Actually, unpin that one. We want this. You've got 3 ports. Now, I just happen to know that 3 is the target chip, 5 is the E4 chip, and 6 is the host chip. And if you look at these instructions, this number in front that you pass to the instructions are which port number. So if I go over here to array forth and I say 6, oh, well, I suppose self-test. That will work. And if nothing is happening on the screen, you're in trouble. It's not working. Try again. And then try again. And keep on trying until you finally give up, and Greg or somebody will help you. Their help system is pretty good. Usually it's Greg. Somebody else will chime in. There's a few people watching their helpline. And it runs through a bunch of stuff. I haven't really looked at what it's doing, but you're watching for these numbers to be changing, some numbers to be changing, and this item will turn to OK when it's done. And it takes it a little bit of time. And that tells me the host chip is OK because I used a 6. I can also do a 3 to check the target. They also have an auto test. Where were we? Yeah. An auto test, you pass it the host number, and it will check both chips, which is useful too. Checks that communication. And that tells you you've got a working board. Now, I do want to mention this paragraph. It talks about changing the parameters. If you go into one of these properties, port settings, advanced, they're going to want you to change some of these numbers. And they've got fairly good reasons to do that. It works better if you do. So you do that on each of the chips, each of the ports. And you just follow their instructions, and it's fairly straightforward. It works for most of the, or all of the versions of Windows that I've seen, that I've tried this on. You just follow all of these instructions. And then you're basically set up. You can read about all of this other stuff. It's interesting. Not always useful, but interesting. The next one is the DB. Data book. I'm not sure what DB stands for. Yeah. Yeah, good. Okay. This talks about the chip itself and gives a very nice document that doesn't fit on the screen, showing what each of the 144 CPUs, how they're organized. And you basically have 64 words of RAM, 64 words of ROM. I/O logic, COM ports, I/O control. You have a return stack, both a return stack and a data stack. They're both the same size in their circular buffer. They are circular stacks. In other words, there is no top and bottom. There is only a current pointer. But the data stack has both a, where is it here? This is the return stack. The return stack only has one register, which is effectively the top of the return stack, or R it's called. The data stack has both a T, which is the top, and an S, which is the second. So in effect, the data stack is 10 elements deep, and the return stack is 9 elements deep. And you have to remember that only 8 of those are circular. So it adds to makes an interesting game you can play on the stacks. And they're fun. There are some examples of that as you get into the code. Otherwise, that's all you need to know about the chip at the moment. That's the layout. This will also tell you about all of the instruction sets and everything, the various differences in the chip. And we'll get into some of the different pieces of the chips in a moment. This is a poster. They've got a very nice poster. You'll end up referring to this a lot. That of the chip, it's organized in 18 by 8. Yeah, 18 by 8. And the outside pins have various things on them that you will have to become familiar with. Some of them are traditional GPIO lines. Some of them are analog lines, like there is an analog line that's also got a GPIO line. Various and sundry little things. Each chip, except for the interior chip, all of the exterior chips are relatively unique. There's some of them that are very similar, but a lot of them are very unique. And you'll want to get to know what each of them do. And at the bottom of this is the instruction set and some very useful things that, nice hanging on the wall. You will refer to this screen a lot. It is very useful. Then, the next nice little picture that they've provided for you is this little thing, which is just a grayed out image of the chip. This is for doing floor planning. Floor planning on the GA144 is exceedingly important. You need to know the flow of your data. Without the flow of your data, you're going to do nothing, because everything is just a flow from one chip to the other, or from one CPU to another. You need to know where your data is flowing, where your work is being done. It is very critical. So you use that. Lay it out. Figure out what you're going to do. Lay out what you're going to do. Write it down, because it's a real pain remembering what it's doing as you get deeply involved in the chip. Try to figure out what the layout is. That's useful. The DB03 is the evaluation board reference, and that one is, again, tells you a lot of the things about the board, but the most useful thing that I have found here is way down at the bottom, is the schematics. Even though I'm a software guy, I like reading schematics. Schematics are very useful and tell you what's what. this is another window that I have open most of the time that I'm working on the evaluation board, is the schematic. And find out where the pins are. Very, very useful. So that's what you do with that document. And the last one of their documents that you're going to spend a long time with is the user's manual. This is what tells you how to work with ColorForth. ColorForth is a rather interesting beast in that it uses a Dvorak-like keyboard. If we go into Edit, now we're in Edit, and if you note, you see down here at the bottom, this is what the keyboard is. Forget what your keys are doing, what your keys say they're supposed to do. This is what they really do. For example, the R moves the cursor, see up there at the top, from one word to another. Word. Word. It is word. Correct. And L means left. You will see this LUDR many, many times. Memorize it. It's left, up, down, right. It's the way the chip works. And you got to know it. So that's right, that's left, that's down, and down isn't really down, and up's not really up, but it sort of is. You have to get used to that and how you change everything. I have a hard time with this, but you have to do it. It's the only way around. Well, it's not the only way. I will be showing you another way. And you have to have an escape key. Escape is your only way. No.
This is floor planning space, right?
No, this is source code.
Okay.
This is block 18 of ColorForth. It is what loads ArrayForth. This is the first screen that happens. The blocks 0 through 18 are the kernel and the font table. This is the first source code in the ColorForth file. You can't call it ASCII because it's not. It is binary. It's color-coded. The user's guide is what tells you how to deal with all of this. It tells you, we go back there to the user's guide. This talks about all of what I've just said. All of what I've just said. And this talks about the keyboard. There's the keyboard. And there's the keyboard. The actual keyboard. It's fun. It's just another little piece of this. It does a bunch of other things and tells you how to get around, how to work around with this editor. I'm not going to go through everything. I'm not real good at it. It's a struggle. But Chuck believes that you need to learn this. And we don't disagree at the moment. Now, this is the next thing that this will give you. To get out of there, you press dot. You need to say QWERTY over here, and now you've got a keyboard. And if I say SO, I've got a simulator. There is the chip. Up here in the upper right corner is the entire chip. The part in blue is these nodes over here. These are each of the nodes. This is the bottom left node. The X mark says which one is being displayed over here. This is the stack for that chip. And I can say, we'll start running. That was a single step. Notice here, these are the step counters jumping. And it's not doing much right yet. So I'm going to say go. And now it starts going. The number down here says how many steps at one time. And if you think this is slow because you don't really see much happening, although it's starting to move across the screen, you can, down here, this plus says go up by 100. And now it goes real fast. And that's it's a crawler. It's what's called a crawler. It's passing the program from one node to the other. It's one of the simplest examples, and the most ingenious part about the chip is that you pass code from node to another, from one CPU to another. You pass it in the code, or pass it in the stream. And it's a neat way of programming this chip. But that's the simulator. Again, spacebar gets you out of it to a QWERTY. The other thing that it works best to go up to the top, I think, and practical example. If this is the first time you are looking at this board and this chip, follow this practical example. It will tell you how to make it work. And it is exceedingly useful. It tells you about wiring up an LED and how you talk to the interactive environment that talks directly to the board, to the chip. From here, now if we remember what we're doing, oh yeah, that's not a good way to do it. Let's see if we can do this differently. Oh yeah, that's going to go to infinity because I'm screen sharing. Let's turn it off of screen sharing, and that means minicam's dead. No, that means Droid Cam is dead. So we need to go over here. Where are you? That screen. Stop and kick him again. There we go. Now we're alive. So even though I have a whole bunch of wires on connectors up to this is a row of LEDs. And you notice that you probably can't tell, but they're just slightly turned on at the moment. Not very well, mostly leakage current, because they are 3-volt LEDs that when you're outputting 0 to the pin, almost are off. Not quite. They're close to off. If you turn the pin on, the 1.8 volt pin on, then they light. I think, if I have the right. No, that's not true. No. At one point, when the pin is on, it is leakage current. It means the other side of the LED is on 3 volts, and the ground pin is the one that we're moving. Therefore, when you turn the LED off, or the pin off, Now you have a good 3 volt to ground connection, and you get a bright LED. When the pin is high at 1.8 volts, it's almost off. It's sort of off. It's better than on. You can tell on. But because they're 3.3 volt LEDs, it makes life interesting. So now if we go back to our instructions.
Not quite binary logic.
It's not quite binary logic, but it's a good representation. For government work, it's fine. So we're going to go and do this 20,000 hex IOR store. Well, actually, first we're going to do host load panel. And there is the interactive panel that you will use. The stack is up here, and these are paths. You got to learn about what paths mean. This is memory. We're in, I think, we haven't said what node we're in, so I'm not sure what node this is at the moment. I think this is the active path to 608. We're going to say talk 0600 hook UPD. And now we are talking, you notice that now we've got a 600 down here. We're in node 600. This is what's in node 600, nothing really. We're not using, the chip is not running itself. We're just doing this statically by using this IDE. And then we say 20, well, first we've got to talk about hex. Hex is rather fun. Everything that if we type a number right now, 100, it is 100. It's in decimal, but if we say Alt, and I have to type function and F1, notice that hex came here. Now I have hex, and if I say decimal or 10, Alt, function, F1, now it says 16 down there, like it should. So we'll switch back. We're going to want to say IOR store. And now if we look back over at our camera, you notice an LED's on. Kind of hard to see, but that little LED's on. We just turned on an LED. We made things happen through the chip, through the IDE. It's good to know, good to experiment with this. There's many ways that I've used it. It does add a significant overhead and rules that you've got to follow to keep it going. But it's a useful exercise so that you know how to do that. And then it goes into writing code, and maybe I can still run some of this. No, I can't. That's right. Because they're assuming that you're doing this on the host chip. I'm doing it on the target because that's, as I said, where I operate is on the target chip. The host chip has a few restrictions that I didn't want to deal with. So I dealt with on the target chip for everything that I've been doing. I've done quite a few demos. I did Maker Faire a couple times with the board. They're online. If you look through the SVFIG meetings, One's called Initial PWM, which is taking this PWM demo and adding a pop to it. It almost worked. It was pretty close. For Maker Faire, it was fine. I did another with the smart board that I didn't quite get accomplished anything, and now I'm back to the evaluation board. And I can say, remind everybody that this is the club's evaluation board. Club owns it. Anybody wants to borrow it, they are free to. I'm not using it at the moment. But, and you'll notice, oh, we should explain those scope pictures. We only did the 20,000 IOR store. There's also one 10,000, 30,000, which is weak pull down and drive pin high and high impedance. You've got different ways that you can talk to an IO pin. And I'm assuming that's what these scope traces try to show. I'm not a scope guy, so, and there's the PWM. I like Ting, don't own a scope. So, or I did actually own 2 little ones, but that's another story. We don't need to talk about that. So that's the end of that. Now we go back to, where was I? Start here. The other one is that link that I have here is another thing that I did when I first started with Intellisys, with John's help, that we played with a disassembler. If you remember right, an 18 list. Oops, I'm in hex. List. Remember right, I said this is not ASCII. This is certainly not ASCII. It's actually Huffman encoded, mostly. And I made a decompiler for this to ASCII. And it's a full round trip. It is working with ColorForth now. It does very, very nicely to go round trip to ASCII back to ColorForth. And
So to do Huffman encoding, you have to know sort of frequencies, right?
Statically assigned.
Statically assigned. From which date?
Presumably from Chuck's earlier source code.
yeah,
So they just say, oh, you know, we just know from experience that letter V occurs this frequently. Okay.
Yeah, it's
Yeah.
not true Huffman code.
It's not true. Yeah, it's
Big Close, Chuck did a lot of frequency studies of programming, you know, his fourth programming, not just general English, and picked up what letters he wanted to be 4 bits, 5 bits, and 7 bits.
right. It is almost a strict lookup table with some gymnastics. It's not straightforward code, how to get back and forth. And every so often, in fact, every so often he changes, he adds another feature.
We've changed the tags.
Correct,
Haven't changed anything else.
correct. It was only some of the gymnastics that I had to play with over the years.
One block of code has both ASCII to ColorForth and ColorForth to ASCII character translation.
Right.
The words fit in one. The words and the tables, translation lookup tables, fit in one word in one block.
Yeah.
So it's not very big.
Right. And the characters haven't moved. No, I don't think.
What we did do is original
Can't remember.
OCAD table had built-in weirdness because the GDS only needed a couple special characters that he hadn't originally included. So his ASCII, his color port to ASCII translation made those, I mean, J went to X, I mean, some funny characters changed for GDS. Since then, we did move that off into the OCAD section, and we have a real true ASCII translation now in the base part now.
Right.
But that wasn't true at the beginning.
Right.
When we first started.
And so it's been relatively stable, but every time they release a new array forth, and they're on 2B now. I don't know how many releases they've actually had, but they change stuff. They are moving this system. There's work being done.
Oh yeah.
And every time things change slightly. So I use this translation to help me manage my code. And this is a difference between, this is the newest version, this is the last time that I worked on it. And things change. This is how many sectors to load, that says how big color forth is. It grew a little bit. Just a wee bit.
Doubled in size?
No, not double. 271 from 255D. Yeah, it got a little bit bigger. And this is all the kernel. This is part of what I added since I was at IntelliSys, is this is all the kernel. I wanted a full disassembly of this thing. And then some tables.
Oh.
Hmm? Yeah. And it is married, hard married to x86.
What is in the kernel in the image is the standalone kernel.
Correct. It is not what's running on Windows.
Yeah, what's running on Windows is a whole separate program.
Correct. 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 With a GUI, obviously. The GUI is not in ColorForth, although you have it looks identical.
It looks identical.
Yeah, it's the same thing. And yes, as I said, there's a character table, a font table. It's there.
You want to change the font?
You can change the font.
This font table.
Can you what?
Is it compressed? I mean, or it has to be decompressed because it's directly referred to in runtime?
It's direct bits that are put out to the graphic, to the screen area.
Nice.
And there is block 18. And you note, and there is the version number. 2B is what they released recently. And I was working on 2A. All my code's in 2A still. And this tells me exactly what the differences were. And you look at this, and what I tried to do was make this actually readable. What John and I actually tried to do. John did this before I even started. He had this already started. And it's real readable. It's not bad. If we go back here to, there's the array forth.
ColorForth to ASCII, and you did it the other way. Or
yeah, I think you went to ASCII and I brought it back.
Yeah.
Right. I made the round trip. A couple times. The kernel one was even harder.
Yeah.
Round trip. That one took a while. But it's not bad. Almost looks like Forth. Sort of. And the reason that some of the highlights in here.
Another advantage of this is you can use this with a revision control system like
Correct.
Absolutely.
That was my big thing, is I wanted to be able to use it with revision control, and I wanted to be able to do this. I want to know diffs.
Yep.
It's not good enough for somebody to tell me, well, all I did was... Okay.
Quite that simple.
It's never that simple.
There's a great book on hardware debugging. The title is something like, I only changed the software, why did the phone catch on fire?
That's a nice book.
Yeah. And 200, block 200 is where you load most of your application, your load block is. That I can probably get away with putting in. There's no conflict. 202 is where you have to talk about where you assign the port numbers for your UART. The ACOM is the host chip, and that's a 3, and CCOM is a 5. It's not where I have them at the moment, but this is where, if you're going to change different ports, this is where you need to change them. That's all I've got there. And you can see they add bridge, and they talk about that in the release notes. Bridge is now in there, which allows you the IDE to extend to 2 chips. It's nice. I haven't used it yet. I don't know. I want to get up here to, I think it's 8 some.
What is a block of code? What is the definition?
What fits on a screen?
24 lines?
No. Don't think in characters.
1024.
Don't think of what a bytes. It's not. It's a screen. It's a screen. Right. It
This
is.
definition is exclusive to the OCAD.
This is exclusive to color forth.
For example, if you were working in Big Fourth or any of its relatives, a block of code would be 16 lines of code by 64 characters per line. And it might come with a shadow screen as well.
And I can't remember if there is a fixed size.
There was a what?
A fixed size of the blocks.
Oh, yeah.
Yeah.
They're all 256 words. They're
Yes.
They're
There.
1K bytes. You know, the 32-bit words, 256 of them. So it's 1K bytes. However many lines that is depends on your code.
Right.
If you make it longer than the screen, forget it. You can blow stuff up.
Right.
That's the buffer overflow issue.
It's Huffman encoded always.
It's always
Yeah, so
encoded.
one on-screen word corresponds with one word in memory.
No.
The first 4 to 7 characters of that word correspond to one cell in memory, yes.
Right. It sort of is a one-to-one, but
1-to-1.
it's,
And
you can blow up the screen, basically.
every red word starts a new line. You can force new lines,
Yeah.
and you can force red words not to start a new line.
Like, these guys start new lines.
You can have a lot of short definitions that totally fill up the screen, or you can have one definition that runs out of the 256 words before you get to the end of the definition. Both things have happened in Chuck's code. Somehow, Greg, in the listing that we do in Colorport, I added the ability to show how many cells were used in that block.
Yeah.
Greg didn't think that was a useful piece of information, and so it did not get released. So things that add. Along with a whole bunch of other stuff so that you interact with the software simulator in the same fashion as you interact with the IDE.
Right.
You don't have to learn two different methods to use the two different tools. And actually 3 tools. I mean, you use the same interface and you have the same source, you're processing the same stuff for creating a ROM image as well.
Right, right.
So you got three things you
Right.
might want to do with your code.
Right. And I've got 2 of them at least. I don't think I did the streaming.
Uh-huh.
Yeah,
They're
yeah.
interchangeable. In fact, you probably have not added where you can interactively run the simulator.
Oh, yes, I have. I did do that one.
Okay.
That one is useful of when things don't work, go back to the simulator.
Exactly. Charlie and I did that. We worked through a whole bunch of stuff there that's really cool.
Right,
But
right. Because you will get yourself into a corner that it won't work.
that's right.
And that's where the simulator is your friend. Now, you don't want to go forever writing code in the simulator and assume that it's going to work on the chip.
No.
That will also burn you. You have to test on the real hardware,
Yes.
especially if you have timing loops.
Communication between nodes cannot be accurately simulated in the software simulator.
And all of your timing,
Right? In any practical software simulator.
right. OCAD has a simulator.
The new one, well, we got a hardware simulator that runs about 1 million times slower.
Yeah.
But we do have an event-driven software simulator
Okay.
rather than one in lockstep. And it's given rough numbers for the amount of time that
Oh.
code takes.
Oh.
So it's doing that. It runs all that really nicely. It can have added to it, the software simulator, the changing of a node's timing because of temperature effects. That could be added, but already it's going 10 to 100 times slower than the current software simulator.
Right.
Sorry, it just...
Yeah, it's that time difference on the real chip that will eat you alive.
Yep.
Because it changes over time.
But doesn't change logical result.
It does if you missed your window.
If you missed a window, you can change what's
Right.
done.
It will stop working.
Yep.
If you haven't done your software with wide enough windows, it will change your system.
Well,
If your constraints are too tight, you will never get it to run on the chip. And you have to loosen your constraints.
Michael came up with some guidelines for communicating processes. Jeff wrote a whole paper about communicating processes of instead of input, process, output, it really needs to be done output, input, process so that you can assure that every node is waiting on the same edge, basically waiting for waiting for signals in the same direction so that you can't get conflicts.
Yeah.
There are also gotchas because you can write to multiple addresses and read from multiple addresses. In fact, you can read and write to the same pair of addresses. Say you're coming in from the left and going out to the right. You could read them both. So you only have to have a single dual address in a register. You don't have to take up 2 address registers.
Yeah.
You got both addresses in it. So you write to both ports and read from both ports. And if the guy on the left is always there and you're waiting to read them, then the fact that you're reading on the right doesn't hurt because the guy on the right is not writing yet. But then when you write, you're writing both directions, and if the wrong side of you is reading at the wrong time, you get out of sync, you can totally hang because you've got two guys writing at each other, two guys reading at each other. Two notes, and it'll stop because neither one can get satisfied.
We're talking about communication between cores, right?
Yes, within a core, it doesn't, the fact that the timing changes doesn't change anything. It can't, because it's purely sequential within a single node. But between nodes, you've got the possibility, if you have multiple nodes communicating to a given node, the asynchronous can bite you. You can get to the point where you're both trying to write each other.
And that approach, output-input process, doesn't sort of guarantee that you won't be...
It doesn't guarantee, but if you've got something that is flowing through, it forces the
Introduces synchronization.
communication synchronization to happen, yes. Yes. You've got to know the flow.
I'm trying to understand that phrase. That's all.
Yeah.
I mean, it's very big,
Exactly.
it's very loaded phrase.
It's very loaded. Yeah.
Basically communicating sequential processes, and it's describing that block,
Right.
situation.
And then it's further complicated. Yes, the communication, there are Schmidt-triggered stuff on there. Is there? Yeah, there is a little bit, so that you get some hysteresis, but you can still have metastability because of reading and writing happening too close together. Let's not get into it.
Yeah.
What will happen anytime a chip changes, the design changes, these things get modified.
I'm afraid practical necessity forces you to get into it because you want to be able to produce predictable results.
Which requires some synchronization with the outside world.
Right.
As long as it's inside the chip, asynchronous and going, all you're worried about is getting it done, but as soon as you want to talk with the outside world, serial port, whatever you absolutely need, predictable results, yeah.
Now, because of this problem, one of the things that I did at Intellisys was making timing diagrams. And this is some code that at that time pulled out of the simulator. I haven't ported it over to the new simulator, but allowed me to, and this is actually describing an FFT. This is how an FFT works.
Pretty complex algorithm.
It's a very complex algorithm. It took a lot of exchanges between nodes to make it happen. But this worked. It took the diagram to make it work because it was messing up. The thing messes up. There's a lot of communication between chips, and you've got to have the windows to be able to afford that. But that's typical. This is all very typical. The chip is hard to work on. But it technically can do something useful. We've made it do things that are useful.
It has a very reliable 1K, 10K UDP interface, all in software.
What is 10K?
The
Battery running low.
the Ethernet
Oh yeah.
and array included in anybody's chips. They have to have the original 10K instead of 100K.
Right. It's standard T kind of feedback, right?
Yeah. And so it's
Yeah,
all.
I read that.
Greg wrote the stuff. It's all in software, bit banging. got a single crystal in there, outside world, that they're pinging that to get it to oscillate, resonate, and it ran for like 9 months without a single drop packet.
Cool.
For Greg's been doing this stuff for 20 years, and that was unheard of from any other commercial chip stuff.
There are ways to get around the difficulties.
Yeah. So you can have reliable kind of configuration of software across the course of the chip.
Yes.
Which allows you to work with arbitrary input data and process them.
Yes. Yes. You can.
Yes.
I hope I can.
It is all possible. You have to remember that the main premise of fourth is that you can shoot yourself in the foot.
Is it that main?
No, it is that you will.
You will.
You will shoot yourself in the foot and then get over it.
I've been around long enough to remember Mitch Bradley's little cutout cartoon with the guy on a crutch and missing half of his leg. From where they shot himself in the foot.
Yeah.
But it requires, this chip is hard to use. It requires really jerking, pulling, stretching your thinking in the different directions. Chuck's, I just reread, what is it, Programming Mastermind or something like that, a book about the dozen or so people that have come up with computer languages. And in it, Chuck Forth was for him, and he's smart. He's happy that people have used it, but his way of solving somebody's problem is basically to rethink what they did. And if he can't write a program to solve the problem that they present to him, he changes the problem and tells them that they're doing it wrong, and he provides a solution to something that is better than what they had proposed.
Mm-hmm.
But he changes the problem, and the issue, he would not use a standard protocol. He would change it.
From my experience, I suspect it's not quite accurate that he
pretty much wrap
solve that problem. He just didn't want to solve that problem in that state, that formulation, because he felt that problem is wrong.
It's hard to tell with Chuck whether it's couldn't or wouldn't.
Yes.
I've hung out with him enough years now.
It's quite often possible to tell the problem is solved.
Yes. That part too.
Yeah, the P equals
P and E stuff, yeah.
The fact that you can provide some example is not very relevant right now.
Actually,
Quite often in
Let
practice,
me while they're talking, let me get over to
in our practice, we don't do P versus unpredictable to other people.
It is. It is a jet engine with no governor.
It's jet engine with sort of very different principle of operation.
Correct. Correct.
See?
Yes.
We know that
And
it's like
it will run
zero
fast
drive.
enough
Yeah.
that it will blow itself up.
Yes. But we really want to fly.
Oh yeah. But I've blown up a couple.
Fortunately, we have like infinite supply of them.
There's a good supply of them. They're not unreasonably expensive. I'm still in. I'm still alive.
They had enough to justify that one layer, I forget how much it costs for another brand, but it wouldn't be that.
What do you mean? Please wait. There we go.
To their application. But right now, the arm is maybe almost a tenth of the size of the RAM. So, it'd be better to have RAM in there than not, but sorry, there's no reason to put that in RAM. Make the door
Camera back up.
Anyway.
And then, so I monitoring as a service.
Haven't you messed with the 144 or the what's this part? I think you had played with those.
That's pretty much what I do.
Because they have those
No, that's for ourselves.
demo
Eventually, we're gonna open it up.
C24 things that they're almost giving away. They're the ones that were on the USB stick.
For the time being.
A long time ago. Really?
When you type words in the
It's just a matter of-
force prompt,
We know we
you list built-in kind of programs and those programs which you, I mean, routines which you added. Right? So when you, I mean, keep creating kind of programs, short programs and bigger programs, like most programs which we use other programs, we just add to that flat list, to that flat dictionary of words, right?
Yeah.
I mean, keep thinking about built-in 32 commands of this chip as a assembly of this chip, as a like machine, even though it's
It
four,
is very definitely a machine code, yes.
which is irreducible kind of set of those words which are just built into chip.
I love what generate C virtual machine. So that people can program.
Back alive.
And again, the issue is not so much doing the code, but it's partitioning, factoring the problem into these chunks that are going to be big. And Jeff, I would like to see, hey, Dennis, I would really like to see, as a tool, Jeff had worked out, he has some of the stuff worked out for his communicating signal
I was
process.
just gonna showcase it.
But to have that as a program in Array 4,
I got it too.
that
Very, very simple.
you just, you make all the communications, you set it up with a node.
And turning.
And you guys with,
But,
yeah, had done stuff like that, assigning things to nodes and doing the layout.
Well, where I saw jump power the chip, and I haven't talked up on the guy that's was talking about power the chip and thinking he can use it for a service.
Right.
And
Just recently, yes.
I haven't spoken up yet. Because what he really is talking about, he's talking about a street. The question is,
We could go to the Stanford Shopping Center, where Max's is. You could go to downtown Palo Alto, where there are a number of interesting places.
you put everything in the
Piece
street.
of my heart, Euro.
It is a reprogrammable. Flips the bits. He's got the right idea.
Actually, they do. We could go to the Sundance My Company where there's
And you put your code right in there. I'm thinking that we're really.
And that's where, that's the thing about a car.
I would go with you.
If it was, as the prerequisite set up for, to point ahead, specify your street, then it is.
Is it a stable place?
I'm hoping that
Constant overhead.
Do you have like a gate there, or
I
just
have
look at
my
Single overhead.
friends
To send a packet anywhere in that street.
I had asked a separate question about, is there also a source of money?
Oh, yeah.
You have a sink, now you need a source to match up.
Well, I'd like to. And if I was really simple with it to work out, I would really make it to max out my social security. I think I'm okay, but I'd like to.
At what age is that?
70.
Oh, so if you retire at 70, that's the most you can get?
I think at age 70, they say, here's your social security. Allow you to
Uppercase, lowercase,
get more money.
in and out,
So,
and.
I'm not sure that I actually understood.
Oh, that is so programmable. And what he did was he had a little translator to translate this
Yeah, well,
into executable code. And so you can just write that notation and have it be code, and you set up it's a very collapsed notation with a number and a program, specify you want to do it that many times. Letters specify specify one of the directions where you're going. Uppercase and lowercase to say whether it's coming in or going out. So you can have stuff go out and come back in on the same port. And his algebra handles it. What is algebra? Because when you work this all out, you can execute it to prove that it will communicate. And then all you've got to do is assign the different parts to different nodes and make different communication going between the nodes. And then the processing is when you set up all the communication with no processing, then you just fill in the processing that each node does. So he gives you, you put out your
wait a little while, all it's in the box is a bunch of cells, it's not recharged in 5 flashlight batteries, 12 of them, or whatever.
Yeah, it sounds like enough energy.
That's what you need. Something like that, separate out,
Battery dumps.
solving the problems.
About
300 watts.
It's yeah, it's all about it.
And the way I can program is you figure out how to by moving the restraints. You move the restraints, and you can solve any of these
Modified, you can't ever remove them all.
You can't remove them all,
So let's say that otherwise, it's really flat.
There's a very good resource.
Computers. They have enough to.
Turn in the card deck and the next day get it back, get the crystal back. So you do most of it. You have a lot of head time. The opposite to the way the works well. Or you have a whole bunch of free time needing so much head time. What I discovered was that when I started investigating all these different languages and relationships,
I use this kind of battery or some aspect.
I didn't care about solving problems.
Basic.
I was just looking at ways to do it. And the interesting thing was if I could choose a set of planks, or constraints that were planks of throw, but a set of constraints that were useful in the real world, that matched up the problem areas in the I had a useful problem. And so I went to figuring out useful constraints.
When you pull your battery,
And
it will keep the
so I, trying to find the ones that didn't need it.
the other, does the cigarette lighter work is the accessible, then it could put it accessible or pull back.
Problem is, it just has on street right.
In that class, except for report. Masterminds of programming is fascinating.
As I remember,
All of the languages in there were developed by
it was this
one or
jumping retreat on the battery, jumping
very small.
They recommended
It wasn't a committee
for
putting together. That's why I don't believe Ada is in there. Everything because it was designed by everybody. But all the ones in there were one or possibly two people.
Like that way. No, that's, you know.
Bringing in Bochi and her.
These are, of course, they're still under a key.
Oh, that's why I don't know. I don't have a
See,
PC.
and my car is.
All of them. The roads and some industrial, went by academic history.
At this point,
I think working class came right out of the box.
We only want
It's the only color language in there, all the rest are like.
So they have this scale complexity or so Jupiter.
Same way hack is nice.
I think it was
They're all
the last mold.
I can tell you squeeze what doing Java and Minecraft and you see all this crap at 5, 6, 10 years old as they get fed up with the rules and limitations, you know, time to do.
There isn't many alternatives.
I almost saw the doctor.
There are not many alternatives
The BBC
that don't have to be on the platform. Now, or if you
In fact, it's today.
just recently have more activity online,
Yeah, it's a lot.
the wearable source, you have the other no and space needs battery.
How about all the stuff that have no batteries?
What time is it?
That are.
I don't know.
We're talking about energy reduction.
Energy harvesting ones are going to bring it even further.
Yes, yes.
1 minute warning.
Or so. That's the problem.
I'm hoping a couple versions.
This is the
Slides.
I'm just gonna show,
the new
Wow.
for real. The changing magnetic state.
Okay.
I was looking up different things.
there's a website called the Memory Guide. Okay. And it's like everything going on.
Yeah, I've seen it.
State memory.
It's done, yeah, really well.
Yeah. Everybody in the industry, who's by who.
So it's not
Pretty interesting.
pretty heavy code. It has.
Losing power on
So.
Using the electron spin to torque.
All right, it is the appointed hour.
Alright, so
You, get a mic. Dennis, reappear.
turn the
As if by
fire
magic.
hose on. Point the camera.
I wanted to say, if you need to pee, you might have almost a chance. If you're not consuming a soft drink, you're contributing to the collapse of the U.S. economy. They're in the red cooler.
But if you're
Help yourself.
consuming soft drinks, you're contributing to the environment.
There you go. So, it's over there, I'm not saying it in a unique. I did want to say, however, you know, a little earlier we saw an SKC, a cartoon with the universal adapter. You can actually buy this accessory for the universal adapter box, which allows you to jumpstart your car from your pocket USB power supply. I really wanted you to know that.
Can I jumpstart Tesla?
That really exists.
And how many fires did it start?
It depends. I don't think there's any software in it.
The question is,
What's the voltage difference between
It's one of these things,
and hooking
but
up
it's
to
got an adapter so that you can charge a battery on your car. I'm sorry, you didn't left your lights on.
Supercapacitors make everything better.
It charges your car battery a little bit. So if you put your 5 amp hours or not locked, suddenly you can maybe start your car. If you're really lucky.
I don't write very much. I know, but
If you want to.
I'm lazy. I'm basically a lazy programmer, that's why I use Fortran everywhere.
It's written 45 or 6. And I've never.
I forgot to put the source code on the laptop, so I had to go clone it.
That was the parental examiner, and he said, deliver this game changer offense clue. It solves the whole.
Which is not cloning for some reason.
This is the RT screen.
Why is you not cloning?
This is x86.
Come on.
Different CPU, different, it's exactly, old storage. This is all given. These are all puzzles that try to solve and enjoy characters as they solve. We're talking about murders.
Some of those are legitimate murder mysteries, some of them are shows crime dramas, pulp fiction, and so on. All
So Steven Spielberg is trying to come up with a minority report.
Oh.
Mission to do it. And I'm going,
Oh, yeah. People are on TV.
Well, if you hold your iPhone up to your eyeball, your retinal scan.
it's interesting. Yeah, I can see that happening. Oh, you are so totally awesome. I can hardly stand it.
So-
More work for me.
So
You just gotta put one link in.
it's
That's why you get in trouble.
I put all of them online.
so I have audio, right?
Somebody has audio, whether it's you.
Okay, I do.
Yes. Is the mic one that's coming out on the webcast?
Well,
They have-
we'll
It's
find.
real hard to monitor that when you only have one person doing it.
Yeah.
So we usually have two. We
I
have two today, so the little bars are lighting up.
Okay, so I'm going to start. So.
Go to a bar and get with us.
Okay, so I'm going to start. I'm going to make this very fast because I'm running out of batteries on my high-res camera, and also because this isn't really like a formal presentation per se. This is kind of like a show and tell type thing. I discovered back maybe a couple months ago, a gentleman by the name of Von Pratt had released a computer science paper titled, if memory serves me correctly, because I'm too lazy to look it up, Top-Down Operator Precedence Parsers. Very unassuming title. And in it, he describes a recursive descent method of parsing, which is not syntax-based. Like most, when you think of recursive descent parser, you think of Pascal and Nick Clausewirth, and you look at how he writes his parsers, and it's, you know, if the next token is procedure, then handle procedure. If the next token is this, handle that. And he does everything this way, and right down to arithmetic expressions. And that has served the recursive descent parsing community quite well for decades. In fact, it is still in very large use as recently as a couple years ago. But for whatever reason, this gentleman, Von Pratt, came up with the idea of, instead of making it syntax-based, let's make it symbol-based. In other words, don't assume the syntax is set in stone. Let's instead be more reactive to what we actually find in source code. And we'll implement our syntax based on context instead of using a context-free grammar. And the end result should be the same. And he's implemented, now in his paper he implemented a means of implementing infix expression parsing. So plus, minus, multiplication, division, that sort of thing, all with operator precedence and so forth. How to handle left associativity, right associativity, that sort of thing. I was hoping to get that far in my little example code, but in the amount of time that I spent working on this, I didn't get quite that far. So what I did, if you'll notice there, I have a very simple subset of the Go programming language where I have the ability to define variables of either int or byte, and I can define a function of type integer. And the only thing it can do is return and add. That's the greatest extent of the language that I implemented. And if I were to actually execute, whoops, before I do anything, I need to actually install it. So if I were to actually implement this, we see that it prints out essentially kind of ugly, unfortunately, but it's a parse tree. So here we see a token unit, meaning a compilation unit in a source file in the C syntax sense. And then we have two things. We have variables and we have functions. Now, under variables, because they are global variables, we see x and y are defined as type int, and then we also have a, b, and c defined as type byte. So that's essentially your symbol table at the global scope. And then in functions, we have the name sum. We have it returning a particular type, although it doesn't indicate which it is, although I already know from the fact that I wrote it that it's returning an integer. Now, how did I build this abstract syntax tree? If we look into source, we find that it's mostly repetitive, and that's only because I have a large amount of unused functionality, or a lot of possible input tokens, but I have only one actual context defined. So I have this token here. This represents either a terminal token, meaning something that actually appears in the source file, or a non-terminal token, which basically means something more abstract, an expression, a procedure, something along those lines. And these are concrete implementations of this, and you'll notice that a large numbers of these don't have any actual data fields. The reason is because token is an interface, it associates a type tag with whatever it's implementing anyway. So I'm kind of relying on that. But for token character, for example, I just store the byte. IDs and types, I just store strings. It's not very sophisticated. I implement white space as a single token, which is easily ignored, and so on and so forth. I won't get into full details. This is kind of the interesting part, though. So whenever we read, actually, before I do this, let me jump down to the actual compile function. Because when we look at the actual loop, we're basically creating a new tokenizer, which is something that actually interprets and lexes the source file. And then we're basically going to go through, and I'm going to say, while there's no errors, I'm just going to skip spaces. I'm going to tell the current token to parse itself as a statement. This is the key part. So I'm telling it, whatever the current token is, execute that token's code in the context of a statement. Now, this is important because some languages, such as Objective-C, have multiple contexts for different tokens. The plus symbol, for example, is very common. Use the plus symbol to declare a class method, or it can be used to add two numbers. How it's interpreted depends on the context, right? So at this top level of a scope, all we care about is how we handle it as in terms of statements. We don't really care about is it part of an expression or not. So that parse statement then gets dispatched into one of these. And the black magic about how this happens is all dependent on Go. I'm not going to go into that now. You can kind of think of it as virtual functions in C++, object-oriented dispatch, something along those lines. And you'll notice that a large number of these are syntax errors. If I were to start a statement with, oh, I don't know, a closing brace. If a closing brace happens to be, you know, just floating out there at the top level of the code, that's obviously a syntax error. So I'm just returning an illegal statement. Other things, on the other hand, which I'll go into, there we go, token var. So this represents the terminal token var that is used to start a variable definition. And you'll notice that we start out by devouring our token, because otherwise we'll end up in an infinite regress. And I'm making token lowercase var, which is the higher level concept. So this thing that we're going to return, assuming that it's syntactically correct, will have a list of variables along with their associated type. So what I do is, in this loop, which is now traditional recursive descent, I basically read in the next token, and assuming that it is a token, which is what this statement up here is doing, this will actually abort, this will fail if it's not a token. I'm sorry, if it's not an identifier. I will append the name of that identifier and I will accumulate that as it goes on. If it's a comma, we don't really care about a comma. Syntactically, you're supposed to have commas between identifiers, but in this case, this is optional. And then finally, if it's a type name, we associate the type accordingly.
Multiple commas in the row are okay.
That's correct. Yeah, so I just wrote this very, very quickly. This is not intended to be like a definitive reference implementation. I had essentially 4 or 5 hours to write something along a Pratt parser. And the end result was I'm able to parse a properly formed, as long as it's an integer, a properly formed Go variable definition. I can say var a, b, c, d, e, f, g, int, right? Or as necessary. But this kind of reveals some interesting things. One is when you go to the lexer, a name is not necessarily a single type of token. You can have an unidentified, never before seen name, which I call an identifier, or if it is recognized, you can have a type, or as you can see at the very top, I can't reach that high, at the very top there, that toke VAR with the capital VAR, that recognizes that keyword as a specific type of token. So the lexer has to be intelligent. So there's some intelligence that you put into the lexer. But that's basically it. Now, this seems kind of complicated, and compared to Forth, it certainly is. But it turns out that Forth is actually the simplest possible Pratt parser, because if you look at the compile loop, so that right there is your top level compiler. This is very similar to what you would find in Forth, which is basically begin word, find if, execute, else number, then maybe a little bit of stack dump logic if you want, and then again, right? That's what, 9 lines of code, 10 lines of code. So the key thing to Pratt parser is you're associating the semantic through a dictionary lookup, essentially. Is if the keyword in this particular context happens to be in this particular context dictionary, then you can execute. Otherwise, it's a syntax error by definition. And it's that simple. And from that, depending on subsequent implementations, different logics, or different contexts. So for example, the return function, I actually did not complete the return function, but if I look at it, wherever it may be, there we go. So for example, here I'm basically just skipping tokens until I find a semicolon. But if I wanted to, I could have, or if I had time to, I should say, I could have put in here, you know, the left-hand side equals token dot parse expression. And so when I execute that function, I'm now parsing, if you will, in the context of an expression, and then I would use proper operator precedence logic and so forth. And it's the same idea. You can actually mutually recurse this style of parsing, or you actually have the freedom of going back to more traditional recursive descent logic. And if you can actually find parts of this in more traditional Forth environments as well. Open firmware, for example, has D number, H number, for example, for pre-parsing decimal or hexadecimal values. S-quote is another word that parses forward in the very, very simple. One. I'm sorry?
Some Forth compilers do the same thing. That's what made Forth totally transportable. Was parsing ahead for numbers.
Okay. But these are very simple concepts. You're parsing just a single token or a single construct, right? All the Pratt parser does is realize we can do more than that. So for example, an Oberon or Modula 2 program starts with the keyword module. Well, that could be perfectly valid Forth code if you have :module, and then that's your Modula 2 compiler. Very simple. And I believe Chuck Moore, once upon a time, had written a basic compiler in Forth using a lot of the same concepts.
Well, it had written 75% maybe of a basic compiler, all the expression processing, none of the I/O.
Right. Yeah, he doesn't need the I/O. It's all based on math. But so I'm kind of this is all written in Go because that's what I work with at work. But I'm kind of, you can see that like I've got gears running in my head. For one thing, with respect to the Kestrel, I did say at one time that I wanted to have a non-Forth-based language so that I can be more inclusive of other people in the community, of the open hardware community. So I'm planning on maybe taking GoSub, my little Go subset language, and it's also a play on BASIC. I'm probably going to take that further, and I'm probably going to implement an actual infix language for targeting the Kestrel once it has the 64-bit CPU finished. So we can expect to find more Pratt parsers in the Kestrel's future. But also, too, I want to try and implement a Pratt parser in Forth itself to try and make the neural net mathematics easier to implement for my game Equilibrium, which you may remember me talking about like 3-4 years ago, that I got it all working except for the AI because the math was just So I may consider implementing a little support tool using Pratt parser, again using that concept. So I think I'm going to play with this a little bit more. This is more of a like I said earlier, this is more of a research thing for me. I'm not like doing a formal, I'm an authority on this type thing. But this is really neat, and I encourage people to take a look at this, and especially in the context of Forth, where the distinction between immediate and non-immediate words, for example, in a Pratt parser, basically everything's immediate by definition because you look it up in a dictionary and then you just execute it.
If you're in the context of a colon, you compile it, and if you're not,
Right.
you execute it.
Right. Now, here's another implication because of this Pratt parser stuff is actually kind of neat, and it'll actually allows this. A full-blown Pratt parser is actually very data-driven by design, since you have dictionaries and stuff like that. That means that Forth is no longer unique in the ability to morph the syntax of the language without the aid of macros. So you have other languages out there like Lisp, for example, that use macros to emulate adding custom syntax to the language. You also have languages such as IO, where you're actually, what they call macros, actually modifies the abstract syntax tree, but only after it runs. So it's basically self-modifying code at that point. What this allows is you can actually write the equivalent of something like :create or whatever, some kind of, or create does. Or what you can do is you can write words that actually just straight up change how the entire language works. You can actually redefine its entire abstract syntax tree if you support that. And it will do so in a manner that allows it to work seamlessly. And you're not relying on macros, and you're not relying on self-modifying code, which means that it's statically inspectable. You can actually reason about the code. So that's something to think about. Anyway, that's my presentation. That's what I've had. This is Pratt parsers. Recommend it. This is some really cool stuff. So. With 22 seconds to spare.
Really? That's how much battery life you got left?
Or accuracy, whatever.
Well, for that segment, I'm down to 1 bar now, so I don't know how much longer. That's true. There's the mic for you.
Save me running over the graphic converter. What's that? Save me running over the graphic converter. I'll make sure. All set. Okay, so after putzing about with it for quite a long time, I've finally gotten G4 to build in Pinnacle, portable Knuckle. So background, beating a dead horse again, is I've talked about Knuckle-related things a bit here, but so backing up, Knuckle or native client is a static verification sandbox that's in the Chrome web browser. There's variations of it per platform, and platform includes the difference between x86, 32, and 64. The core idea is that you've got constrained code, constrained machine code that you can verify at load time is safe. There is an accommodation for dynamic code, but that needs to go through a special syscall where that code too gets verified. So you restrict what kinds of operations you can do, and your I/O has to occur through an API called PPAPI. So you have a region dedicated to your sandbox somewhere in memory. You have code separate from data, and you may not modify the code while you're running, and the code needs to be verified. And there's a variety of techniques that are used to make sure that the code can only write to the data region, and that the code cannot modify itself. So portable Knuckle is an attempt to put on top of this a layer that lets you send a single wire format across that is both portable and future-proof, and does not bake a particular architecture into the web. And portable native client is actually turned on by default now in Chrome. So when you're running Chrome and you navigate to a page and it has a portable Knuckle executable on it, it will just run. What portable Knuckle consists of is it's a variant of the LLVM IR, also called bitcode, that's used as the wire format. Basically, what's done is that it's a sort of a reduced version of this format. It's also not. It's actually not tagged. We finally ended up not tagging the format with the normal LLVM prefix, so it doesn't look out of the box like a bitcode file because it has a different header, but it's the same format. The main thing is that the types have been reduced to normal LLVM bitcode. There's still type information to some degree. It sort of still knows about structs and whatnot. Whereas with portable Knuckle, we sort of boil it down to just integer types and pointer manipulation. What happens is that when you navigate to a page with one of these portable Knuckle executables, it gets downloaded. It gets translated by a compiler in the browser on the fly. The compiler itself is actually running sandboxed inside of native client. So even if the compiler is exploitable, that's not an issue. It generates code, and then that gets loaded. And then it's run within the native client sandbox. LLVM bitcodes is to give you a sense of the flavor of it. It's you can tell you had a C function, it turns into something like this, and so it's sort of on the same, approximately the same level of. It's intended to be sort of a limited register, an unlimited register machine. Where you've got sort of this expressive power of C, and it has a lot of C-like assumptions baked in terms of what a function is and how call frames work and that sort of thing. So G4th is a very portable GNU Forth. Its core engine conveniently is written in C, as our toolchain is LLVM derived. That anything else would be a bit of a problem. It has many different options for how the Forth is threaded. And many of them are portable and are based on computed go-tos, which fortunately we recently added support to Pinnacle 4. Prior to that, I was not able to port G4. It has there's actually two two main versions that I've successfully got running. There's the indirect threaded version where, and then there's also a doubly indirect threaded version, which is actually just because that was the first one that sort of popped up and built. That's the one I've been running. But that's not the only problem you have. So in the native client sandbox, as I mentioned before, your only I/O occurs through this API called PPAPI or Pepper, and Pepper does not look like anything you would normally expect. It's descended from plugin APIs for browsers. It was intended to be sort of a potential replacement for NP API, and it has a very asynchronous feel to it. Lots of asynchronous callbacks and whatnot. So over the last many years, we've been building a POSIX compatibility layer called NACL.io on top of PPAPI. It presents the illusion that your module has certain virtual file systems available to it. So you can have a memory mount or a mount that goes to a thing called HTML5 storage that persists between sessions. We've gotten to the point now where that actually presents a pretty good illusion to programs that run that they are running on something like a normal POSIX system. Because of that, we've been able to have a whole bunch of different ports. I just checked the count before this talk, and we're up to 240 ports. Not all of them build for all of the different variations. We actually build the ports for NACL and for Pinnacle. We build them for, we have several different libcs that we support. We support glibc, we support newlib. Pinnacle is currently newlib only. We also have work on Bionic underway. The different combinations of the ports build, typically most of them will build with glibc, a smaller subset run with, also run with newlib, and an even smaller subset run with Pinnacle. One of the main issues being that with Pinnacle, your ability to use direct assembly is more constrained. We have a continuous build that we have publicly visible of these ports, and all of the builds of them are archived, which is kind of convenient if you want to grab them and play around with them and whatnot. And they blink on and off as things break, unfortunately. So because of all of these ports, we've recently been able to cobble them together into a development environment. We've got another layer of emulation because actually NACL.io doesn't emulate all of POSIX, in particular doesn't emulate processes. So we do a very, very crude job of emulating processes in something called NACL spawn. And this lets us actually string them together in something that resembles a normal Unix command prompt. And as I demoed at one of the prior FIG sessions, we've gotten to the point where you can now do Vim and Make and GCC in conventional NACL, I should say. Not all of the pieces of plumbing for this currently work with Pinnacle, and there's persistent state. I mention this mainly because I'm also going to sort of bring up the non-Pinnacle version of the port in this environment. Okay, let's go and demo. So I'm going to actually, oopsie, let's not change the slide. Select. I don't want to load it here. So if I load it in an incognito window, there's no persistent state, which actually doesn't really matter for this. Oops, and I still opened an incognito window. So if I run an inventory window, it loads and runs. The very first time you run it, if you do run it in a non-incognito session, it will put a little splash bar at the top asking you if this site can store data permanently on your system. And this is an attempt to actually give it one of those persistent mounts. So in principle, if you read and write using the normal fourth file operations, you will be reading and writing to a file system associated with that domain. If you there's a way to go into your settings and blow away the persistent state associated with that, and then it will be gone. Yeah. Yeah, no, that's you laugh, but that is a sort of a broad general issue with that sort of thing. It's something we're going to need to think about long term is how to make sure that your state can live somewhere else too, in order to make sure that you don't lose the world when you lose your browser cache. So you'll notice also at the very top there's some blue, which is just plumbing from some of the GARP that we have for showing a progress bar. The first time you load, you'll see some progress as it downloads. Remarkably, the portable native client executable, which are, I should say, are typically actually a little bit bigger than the non-portable variant. In this particular case, there's something unusual about G4 because it actually comes out, the portable executable actually ends up being smaller for some reason that I have not quite figured out. And so it's about 640K. And then there's also a tar file that currently gets loaded at startup that is a snapshot of all of the stuff that's typically in user share or something or other when you do an install of G4. In the dev environment, because there's a sort of a shared file system between apps, there will be different opportunities to deal with that shared stuff. But for this page is just a standalone build of it, so all that's baked in, and it's getting untarred into a memory file system at start. So that's actually a non-insubstantial part of the initial start time, is that it's fetching that. And so if it has to do the download, it's actually silently doing the download of about it's actually 1.8 megs, which I thought I had gotten it smaller, but that's at least when I looked a moment ago, that's how big it was. You'll notice, in addition to the normal things that print at the beginning of G4, there's some noise there. We have a layer in the ports tree of a thing we call glibc compat, which is a bag of stuff that is all of the things that we have run into that people typically expect in your libc that is not in newlib, and we've sort of patched it up as best we can. And unfortunately, in many cases, glibc will, if a particular set of functionality is not present, it will just give you an error code and quietly set error no. Some of our stub implementations of stuff makes a little bit more noise. We're actually in the process of talking about whether or not this makes any sense, because you get messages like that. The good thing is you know what's not working. The bad thing is that you hear about it all the time, sometimes on every key press if you're unlucky. Yeah. So anyways, the environment is here, and you can type words, and you've got a terminal. And why do I not see the bottom of the screen?
That wasn't too slow.
Sorry, which?
That wasn't too slow.
No.
Oh
no. Yeah, no. I mean, it's so the terminal I should mention is implemented in JavaScript. So it's actually it's actually an Xterm 256 color implemented in JavaScript, and it's the same one that's used in there's an SSH client for Chrome OS and a bunch of others. It's a thing called Hterm, and you can do all the usual things. You can define a word, and you can use the word, and you can print it. The things that don't work that I've noticed, if I were to do C square, something, at least in this particular version, is angry because it prints square and then stalls. The curious thing is that the disassembler did manage to get baked in, so you get some kind of disassembly, but it's the wrong disassembly. So I suspect that there is some mismatch as to what it thinks the arch that it's been built for.
I love how that's done in stats.
Yes, indeed. Let's see.
Work in progress.
Yeah, I would say, considering I got this working, 4 days ago, 3 days ago. Yeah.
It's really cool to see correct this time.
So let's see. So if I go and grab some chunks of code, this is all. It works well enough to do the very basic, kinds of, here's somebody printing like, I guess they have a tower word, something like that. Let's see, the next thing I was going to show, this is kind of amusing, the little standalone environment. That doesn't do much for you. What the longer term vision is that we have this this dev environment. So this is a Chrome app that it's running through the browser. You'll notice I launched it from this app launcher. I could have launched it from in the browser, but it's something that I installed through Chrome, and it's running inside of Chrome. This presents the illusion of a bash environment, and there's a directory structure here. And so, for example, in here I've got the same example file. I can open it in Vim. I can make edits. And then I've installed not the Pinnacle version. There's a bug right now. It's supposed to be possible to install the Pinnacle version. Right now, this in dev environment is a very interesting hybrid. It allows you to sort of intermix glibc and newlib executables and Pinnacle executables, and it's supposed to sort of gracefully detect when you're at the point of going to spawn somebody. Okay, let me go read the headers and figure out what you are and go down the right kind of a load path for it. Unfortunately, something's not working right with the Pinnacle load path right now, possibly because it's only got limited tests around it, and some of them got disabled the other day. So you can, in this sort of an environment, you would be able to, invoke the program and run it. And what did that do? Oh, I see. And the output is strangely intermixed for some reason. I don't know why it managed to print. Oh, maybe that's normal.
Because it doesn't end in by.
Ah, because it doesn't end in by. Ah, yeah. Yeah. So that's kind of the long-term vision. Right now, because this environment is a NACL-only environment, it's tied to being in one of these Chrome apps, which requires an install and explicit step. And there's some good things about that because a lot of the pieces right now are relatively large. In the long run, with all of the pieces of this environment were something that were in Pinnacle, you would potentially be able to have this be at a site. You would navigate there, and you would need to very aggressively cache things and play all kinds of nice tricks if you wanted it to behave nicely offline. But you could provide some approximation of the same kind of thing. And I'm at least nominally working towards that. So that's kind of where that is. As a are there any questions? I had one other little slide where I was just going to show the latest haikus, just because a few more pop up, and if I don't show them, they'll drop off the top. So yeah, let me actually. I forgot actually. I was going to do one other thing. I wanted to talk about sort of roughly what was involved. So. So the ports have gotten a whole lot easier to do than they used to be. I mean, I have ported Vim to NACL about 3 or 4 times, and the first time was just terrible. It involved I wrote my own terminal with raw bitmaps, and I was using some strange IPC layer to send stuff and a different graphics library. It was just and as NACL has sort of bubbled towards stability and whatnot, it's gotten better and better, and our POSIX emulation layer has gotten better and better. And so, as a for instance, in the background here, since lunchtime, I've been putzing around in the background, and I was able to. One of the other things, by the way, I'm bringing up is X Windows, and I've gotten to the point. I don't actually have the X server, but I've got many of the client apps that XI is running, and previously I had only one window manager, TWM, and I just ported FVWM while sitting here. And so the ports have gotten a lot easier. So GForth in particular, so there was a version of it that I had gotten building in glibc maybe a year, almost 2 years ago maybe. And at that time, sort of if you're doing glibc and you changed lots of stuff, you could get it to build. I hit a huge patch, but now let's see, where are we at? Well, so here's what one port consists of. There's only a few files in here, 4 files. There's a package manifest that just describes here's the URL where to download it, what version, what its dependencies are. You'll notice it needs glibc compat, so you can build it with newlib to build in Pinnacle. It needs NACL spawn because I want to be able to run it in the dev environment, and everything that runs in the dev environment needs NACL spawn. And then it's got libtar because right now I'm untarring the user share directory on startup because I wanted it to be able to run on a page. If I didn't care about it running on a page, I could package the user share directory a different way, just for the dev environment, but then it would only run in the dev environment. And I wanted, after having been longing to have that page you go to and that pops G4 for a long time, I wanted that to work. So that's what's in here. That part's the easy bit. This is, there's a bash script to drive the build. One of the things I ran into is I needed to tune down the number of simultaneous jobs in running make, because apparently something in the G4 build does not work when you do J something greater than 1. So that so that popped out. Also, I discovered that in order to get a working build, I actually needed to have a build of the same version of G4 for the host system. The cross-compile is not completely happy if you don't have that, it seems. And further, it needs to be of the same word size, which would seem to be a huge prohibitive thing. Perhaps I have done something horribly wrong, but you'll notice that I'm building, so I have a host build where I basically forced it to build a 32-bit executable, even though I'm, say, building on a 64-bit system for the host. And then once I have that, I could then, there's a bunch of, this boilerplate really needs to go away, but this is basically all the GARP you need to inject the NACL IO layer plus NACL spawn. It ends up being that you need to jam a bunch of stuff on the link line, which is kind of unfortunate. This little incantation lives all over the place in the ports, probably should be moved in one place. This is basically, let me inject this glibc compat include directory and the slide. And I don't know what without check is, but apparently I needed without check. I'm guessing that may have turned off some of the tests. It's funny because in the glibc port that I had about 2 years back, I did actually have the tests running in the build, but it was a huge patch. So one of the quirks of NACL is that unlike a typical cross-well, maybe not that quirky. We have a program called Cell Loader, this is Secure Elf Loader, which at the command line lets you run a NACL executable. It doesn't run it sort of in its full glory, and if you have any sub-processes, things like that, it's not going to work. But what that meant is that I could, if you build a NACL executable, then run it through Cell Loader, you can then, say, run some tests, for instance. The trouble is that that only works if your architecture is capable of running all the different things. So if you, for instance, build for ARM, you're not going to be able to run it that way. And then, let's see, the build is pretty normal, and most of this is, again, sort of boilerplate to, there's an install step that's assembling all the tarball of stuff that's in the user directory and blowing away some things that I don't want, like the man page, and then zipping it all up. So that part wasn't too bad. Then there's the patch that I needed. Most of the things in the patch are actually, I am actually back with the glibc port. I did kind of briefly talk with the upstream G4 folks, and they kind of expressed an interest in me upstreaming, things to fix it. And at the time, the patch was horrendous and huge and poorly done. My still limited grasp of AutoConf was even more limited, though I'm not sure anyone fully grasps AutoConf. And I've spoken to some folks that really should. So a lot of this is there's some little quirks with the with a lot of these ports we really try to do an out of tree configure so that you're not building your outputs into the source tree. There were the bulk of these patches are actually to fix the G4 build, so you can build outside of the source tree. And there's a couple weird ones, like there's some plumbing in the G4 makefile to generate the MS-DOS and OS2 makefiles, because those platforms can't generate them, but those two don't work out of tree. Let's see, what else? The only real meat here in terms of the actual port is there was a place where they assumed they could do some inline assembly even if you were building the generic build, because under certain circumstances it would magically assume that you are a 386 if you look like a 386. And so I needed to turn off these macros, which did happy things. I needed to drop the, this is actually a funny one. This one actually landed as a second change because On my desk building with, so remember how I mentioned there was that host build and then there was the cross build. When I was building the port originally, I was building in a system that still had some version of GCC installed. The builders, or at least one of the builders that we have for the continuous build, was running Clang for the host. And Clang does not like the FF force adder option, which apparently is long deprecated and obsolete or whatever. So, and intriguingly, there was a similar flag that used to live in here that the change log for G4 indicates they dropped due to something similar. So I suspect it's a not altogether uncommon thing. Here I've disabled one test that did not run and was apparently not disabled by that flag. I changed some of the plumbing. This is why I'm even getting an assembler and a disassembler at all. The code to detect what assemblers and disassemblers to bake in had the assumption that if you that you needed to be on the machine type that you were getting the disassembler and assembler for. So it's another cross-build issue, really. Let's see. A couple of flags that made the Pinnacle compiler angry. Intriguingly, Pinnacle does not let you do inline assembly, and it gets angry even if you do inline assembly that has an empty block of text, which the G4 code was doing in various places, rather than just using the ASM directive. So, a little macro plumbing. There was some code path here related to the terminal, and so glibc has more verbose terminal handling, whatnot. But for the new lib version, I had to turn this stuff off, as did apparently Solaris and Win32 and a number of other people. There's a little bit of surgery on the main entry point for an ACL executable with our POSIX plumbing, unfortunately, is not main. We're in the process of working on that. That would be nice if you didn't have to do that. There is a not altogether uncommon trick in many of the ports is to pass the -D into the build and redefine main to be NACL main. Unfortunately, for some reason that I don't recall, that did not work for this particular port. But many of the ports avoid actually having to put that in the patch. And then here's I inserted the line to do an untar of the tar file I mentioned on startup, somewhere early in the startup, and that's the end of the patch. So that wasn't...
So basically you didn't have to go in and change any C code.
No, not substantially, right? But
I did when I was porting G4 to PCOS.
Hmm.
There were certain things that just didn't make sense.
Mm-hmm. I mean, as you notice, the fact that the C command hangs is an indication that not everything is altogether right. I haven't. This by the way was this is the doubly indirect threaded one. I haven't tried the indirect threaded one to see if that one behaves better. I believe let's see. I think there's a direct threaded one as well. That one you need a little bit of ASM for the transition, which is not going to be easy to do in Pinnacle. For conventional NACL, I should say, by the way, a lot of these things you can do. One broad problem with any of these, though, is that because the code and data error are separate, you have to be very careful about how the dictionary is structured. That's that.
My version report
Mm-hmm.
does execute. It starts to execute
Mm-hmm.
in the cost environment.
Mm-hmm.
Just to figure out how to get it going.
Mm-hmm. And one other one I should. Of course, here is an ARM Chromebook just for the sort of proof of cross-platformness. So here I'm going to hit reload, and of course, whoops, I hit reload on the wrong. Oh, and I need to re-authenticate with Stanford because I went away.
So this should actually run on just about anything?
Yes, the one major caveat is so yeah, here it is running on ARM and mobile. So right now, Chrome on mobile does not have NACL or Pinnacle.
Oh, okay.
Yeah, but for all desktop and Chromebook type environments, you should be able to run this stuff with Pinnacle. Cool. Any other questions? One other thing I wanted to bring up briefly was just to show off the latest haikus, because there were a couple of amusing ones. While we're here. there's only a few that are intriguing. So the main the main batch of fun ones is that one of our friends in Russia has shown up with a bunch of fractals, and what's particularly neat about them is if you take, for instance, let's see, this one, and this one, this one, this one, this one. So these are nice and animated. The neat thing is that notice how very small the description is, and what's kind of cute with some of these. Let's see, this one is this is an oddball one, but then notice what he starts to do. Here's oops. So here's the 255 byte version. Yeah, and then they refined it, and now here's the 125 byte version. But oh no, that's not enough, because here is the 63 byte version. So 63 bytes. I mean, that's almost.
Is that static?
That's well, he's counting the number of characters in the code. So the picture is static, unfortunately. So animation just had to go. Yeah, but you know, that's pretty. I'm shocked that you could get any fractal at all in this form in that few bytes. So.
What the code classification?
Indeed, that's not exactly the.
That's a side effect.
Yeah, I guess that must be an L. I hope that's an L.
What do you say?
L or a 1. Yeah, it's
both.
Yes. But make sure folks can see just how small that is. This right here is the code. Yeah, I think those are the only broadly interesting ones.
So what does Google have against NACL on mobile?
It's not necessarily off the table. It's just been sort of it's a tricky thing because with the mobile browser we try to keep it small. So there's that. There's until recently mobile was ARM. A lot of the we needed to make sure we had portable NACL sort of functioning. There are possibilities there. It's you don't want your phone to burn up when you start doing a compile on the phone.
I knew at one point in time the mobile carriers didn't want to be scripted.
Yeah, but JavaScript runs, for instance, so that's not, yeah.
So that's gone away.
Yeah. I mean, the phone browsers are capable of some degree of JavaScript. The other big, and actually this is probably the biggest one. Remember I mentioned that the I/O layer was PPAPI. The whole PPAPI is extension plumbing for Chrome apps. There are no Chrome apps in the mobile version, and so that's another small piece of plumbing that's missing. Yes, so there's no apps even if they're written in JavaScript, or extensions more significantly. Yeah. So.
The other thing too is Apple is primarily concerned about emulators because emulators let you run software that you didn't pay for through the App Store.
Correct.
Yes.
It opens up their App Store that they can't close down.
Yes.
They allow JavaScript.
They allow JavaScript, but only through the web view that they ship. So it's yeah.
They got strong arm for that.
Yeah.
By the people using JavaScript, there's enough of them that they could not say no.
So I apologize, but the camera died smack in the middle of your presentation.
Win some, lose some.